Hello, my name is Kim Olsen. I'm a professor in geophysics at the Earth and Environmental Sciences Department at San Diego State University, and I'm the co-director of the joint doctoral program in geophysics between San Diego State and University of California, San Diego. In this video, I will give you a taste of my research expertise and some of the research projects I have conducted with the JDP students that I have mentored. Some of them are listed here. You can find a complete list of my peer-reviewed publications at this site here. And if you have any questions about the program or potential research projects, please email me at kbolsen@sdsu.edu. An example of modeling of ground motion is the shakeout scenario, a magnitude 7.8 earthquake anticipated on the southern San Andreas Fault in the future. The research into such scenarios started more than 2 decades ago with the Southern California Earthquake Center and the U.S. Geological Survey with the development of source and 3D velocity models. The results of the first ground motion simulations showed unexpectedly strong ground motion amplification from a waveguide of interconnected sedimentary basins for ruptures propagating northwestward, as you can see in this movie here. These early simulations used relatively simple and smooth velocity models without topography and without shorter scale crustal heterogeneities. However, when these features were included due to advances in numerical codes and high performance computing, the effects of the waveguide turned out to be strongly diminished, as you can see going from the early models here to the later models. This is the waveguide amplification here in 3-second spectral acceleration, G's shown here, much diminished in the updated model. The validity of the updated model was shown by comparison of simulated and seismic data from a small earthquake where the waves propagated along the postulated waveguide. And so you can see here the first early simple model in blue, the updated complex model in red, and the recorded data for the small earthquake in black at station RUS in the middle of the waveguide. So here the updated model generates a much better comparison to the recorded data as compared to the early simulations. So in other words, advances in ground motion simulation reveal some very good news for Los Angeles. Within my research group, we have developed a state-of-the-art multi-yield surface Ivan type nonlinear approach to model ground motions in a 3D model, which is scalable on supercomputers. We apply this method to assess whether nonlinear or inelastic effects are important in specific areas, particularly in near-surface soft soils. This is important to know as nonlinear effects can significantly alter ground motion levels. Here we apply the nonlinear modeling to the 2020 magnitude 5.7 magna earthquake in the Salt Lake Valley, which was well recorded by seismic stations in the area. A few near-fault stations recorded large peak ground accelerations, such as LKC here, with the peak ground accelerations of more than half a G. When modeled in the linear regime, we compare spectra here up to 10 Hertz. The observed spectrum at LKC is in black, and the linear result, without including nonlinear effects, is shown in blue. So we are unable to match the recorded ground motions in the linear domain. However, when modeled in the nonlinear domain, we're able to predict the ground motions much more accurately, namely shown by these colored spectral lines here with different parameters of the nonlinear reference strain. So constraining the level of nonlinearity will allow us to predict ground motions from future large earthquakes more accurately. In the Pacific Northwest, the subduction of the Juan de Fuca plate under the North American plate gives rise to giant megathrust earthquakes about every 500 years. As the last magnitude 9 earthquake was more than 300 years ago, the probability of such megathrust earthquake is becoming significant. Several metropolitans, such as Seattle, are located above the subducting slab. To constrain the level of ground motions that can be expected in such event, we have carried out ground motion simulations of magnitude 9 subduction earthquake scenarios in a 3D model of the Pacific Northwest. The depth of the subducting slab, shown here by contours, is well known, shown here in the cross section, and we've designed slip distributions in agreement with constraints from modeling of megathrust earthquakes. The movie shown here is illustrating the wave propagation from such earthquake, where the earthquake starts in the southern end of the subduction zone near the California-Oregon border. You can see the magnitude of the east-west component of the waves in meters per second here using the hot and cold color scale. And the nonlinear effects of plastic strain shown using the green colors. The emerging traces, as you can see here, as the wave propagate northward, show the seismograms that select locations that would be recorded if this scenario took place. And the simulation shows very interesting features such as strong shaking in the Seattle basin due to the sedimentary deposits in the area. Embankment dams are critical lifelines that are vulnerable to earthquake shaking, as failed dams can cause severe flooding downstream, leading to many fatalities. For this reason, we apply our nonlinear code to test how existing embankment dams will hold up in a large earthquake in the future. One example of such project is testing the Long Valley Dam in the Sierra Nevada mountains in California. The dam is equipped with a strong motion array. And we were able to constrain the velocity model of the dam and its surroundings using recordings of small recorded earthquakes in the linear domain. When simulated the maximum credible earthquake in the area, the largest event expected in the area in the future, we get this result for the dam with peak ground velocities on top and peak ground accelerations at the bottom. And we get PGVs up to about 70 centimeters per second and peak ground accelerations above half a G in certain areas of the dam. Our analysis concluded that the dam will likely do fine in such a large event. In order to obtain accurate estimates of ground motions for future damaging earthquakes, an accurate velocity model must be available. For some areas, accurate 3D velocity models are available, such as the Los Angeles and San Francisco regions and many others. However, other areas where future damaging earthquakes are expected do not have such models available. An example is southeastern Alaska, where large subduction-related earthquakes are expected in the future, such as the 1964 Good Friday magnitude 9.2 earthquake that caused great damage in the Anchorage area occurred. One of my projects is to assemble and calibrate a 3D velocity model for this area using comparisons of simulations and seismic recordings for small earthquakes in the area. So you can see here some preliminary comparisons in black of up to 10 hertz seismic waves for data and for simulations in red. Such velocity model will allow more accurate estimates of ground motions for future subduction earthquakes in southeastern Alaska. Thank you for your attention.